Hello and welcome to Midnight Sun Statics tutorial number 2. Today we're going to be talking about joints and specifically joints in 2 dimensions. So we'll be going over first of all degrees of freedom, then talking about different types of joints in 2 dimensions, and finally how we're going to find reaction forces and moments. So in the last tutorial we talked about solving statics problems based on a series of known and unknown forces, right? So say we just have a bar that comes here, and we were saying, well, we've got a force coming in here, we'll call that f of x, and we've got a force coming down here, call that f of y, and then we've got some reaction forces. So we've got, f1, we've got f2 over here, and we've got f3 over here. But in the real world, we aren't just given reaction forces, right? We're given a real physical object, and we need to solve, or we need to figure out what our reaction forces are going to be, right? For instance, in this problem here, if we're saying that we have F1 here in the y direction, why don't we have F4 here as well? And to understand this, first we should go over what are the ways that things can move in our xy plane. Well, there's 3 ways things can move. Either they can translate in the y direction, they can translate in the x direction, or they can rotate about the z-axis, and that's what we've sort of been calling moments, right? Moments cause things to rotate about the z-axis. And different types of joints in the real world are going to restrict different types of motion. And so in statics in 2 dimensions, you'll get these pictograms to represent different types of joints and kind of give you an idea of how they're going to work. So we'll draw out a couple of them here, right? So let's say we still have this same bar, and we still have these 2 forces, f of x and f of y, acting on this point here on the bar. But then instead of getting reaction forces at our points, we're going to draw in some joints. So here I'm going to draw a pin, and it's going to be on some rollers, and then that's going to be on the ground. And over here I'm going to draw in a pin again, and it's just going to be directly resting on the ground. You can kind of perhaps visualize that this pin isn't going to be able to provide a reaction force in the x direction because it can just roll back and forth, right? If you push it, there's nothing preventing it from going back and forth. Whereas the one that's directly connected to the ground, it's going to be able to provide a reaction force in the x direction, right? So this one here gets a force there in the x direction. And then both of these are going to provide a force in the y direction. That may not be so obvious. You might kind of think, well, this pin can just kind of lift off the ground, but that's the limitations of these pictograms. So we're going to say that both of them can actually provide reactions in the y direction, and so that's how we get our reaction forces. And now using statics, we can solve for these reaction forces. You'll notice that both of these are sort of pin joints, and that basically means that they can't provide any kind of moment reaction. This arm that we have here is free to rotate freely around each joint. And so this pin fixed to the ground here on the right, it only has one degree of freedom that it provides, and that's to rotate. And this one here provides 2 degrees of freedom. It can rotate about this point, and it can also translate in the x direction. And that's how we determine what our reaction forces are. They're still unknown, and we then have to solve for them. There's a third type of joint that you might encounter, which is just a fixed joint. So if I have just a bar extending from a wall, and I have a force coming down here, F, this joint here is actually going to be able, it has no degrees of freedom, right? It's fixed to the wall and it can't move. And therefore at this point we have all 2 forces and a moment reaction, and we would have to solve for all of these. Okay, so let's maybe just go through a bit of a problem to demonstrate this. So what I'm going to draw here is something of what we call a rocker. Poorly drawn, but and we actually have some of these in the suspension of Midnight Sun. So this here is going to be on a big pin joint. It's actually a clevis, and we're actually going to draw in yet another linkage coming like so. And this one here is also going to be fixed to the ground. And then finally, at this point over here, we're going to have a force coming in like this. I'll just call that F for now. And then finally, we're going to draw in some dimensions. So I'll just draw these dotted lines to kind of represent the axes of things. And this is going to be 30 degrees. This will be 30 degrees as well. We'll have a right angle there. There'll be a right angle here with this force as well. And then this distance here, let's label these points. Call this A, B, and C. Then we'll just write in on the side here. So the length AB is going to be equal to 1, and the length BC is going to be equal to 3 units of measure. Okay, so now the goal, let's say, of this problem is to solve for the forces at B. So it should be pretty obvious that we're going to have sort of two reaction forces at B, because it can't translate in the X or Y direction. It's fixed there, but this rocker is free to rotate around B. So at B, we're going to have F of BY and F of BX. And then, similarly, we would think, well, over here, and maybe let's label that as well. Let's call that D. We would think, well, okay, well, we should also have F of dy and F of dx. But you'll notice that any force coming out of D, any reaction force coming out of D, has to go through this other arm, and then it's going to go into the rocker at A. And we can sort of imagine that any force that A is delivering to the rocker arm is also delivering to A. So suppose we had, and I'll draw this in a different color. Suppose we had some force acting on A that was going this way, right? Well, that would actually create a moment around D, right? You have this this perpendicular component of this force, and that would create a moment around D. But because D can't react a moment, then this would start to spin. But we're still talking about statics here, and nothing can move, nothing can spin. So what we find is that all the force going into A, and subsequently all the reaction force from point D, from this pin joint here, has to be along the axis of the bar between DA. So we can erase some of these things here, and we don't need to really worry about the reaction forces at D. All we need to worry about is a force that's coming along the axis here of this bar, and we'll just call that simply F of A, because it's hitting our rocker at A. And so you'll notice that this member here that has this force along its axis is called the two-force member, and they're fairly common. Okay, now let's just redraw this because it's getting a little crowded. And since we know what all our forces are going to be, right, we're just going to draw this again just kind of as a triangle, and put in the forces that we need. So we have F of A, F of by, F of bx, and then finally our force coming in here. And we'll just draw on the units. We have 3, 1, 30 degrees, 30 degrees, and this is perpendicular, and this is perpendicular. And this here is still A, B, and C. So first, let's just evaluate the equation of moments around B. That's probably simplest. So if we have the sum of moments about B, with counterclockwise as still being our positive convention, that's going to be equal to 0, and that's going to be equal to 3F minus 1 FA. So then we can say that FA is equal to 3 times F. And then to solve for to solve for FBX and F of BY, we would do, you know, the sum of forces in, that's the y direction, 0, and that's going to be equal to, let's see, I believe this angle here, then if that's 30 degrees, that should be 60 degrees, and that should also be 60 degrees. So in the y direction, we're going to have F sine 60 degrees plus F of A sine 60 degrees, and then plus, and plus, obviously all these are plus, so one of them is going to have to be negative, but because we're just going off of our assumed directions here, plus F of by, and then similarly for the sum of forces in X equals 0, this is going to be negative F cos 60 degrees plus F of A cos 60 degrees plus F of Bx. And you can solve the math on your own. So I hope that's clear, and I hope you understand sort of what our degrees of freedom are in 2 dimensions, and then what joints are, roughly speaking, in 2 dimensions, and then finally how we can take a problem like this and solve for where our forces are going to be, and then take that and solve for the statics problem. And then in the next lecture, we're going to be talking about generalizing this to 3 dimensions, talk a bit about joints in 3 dimensions, and then hopefully you'll be ready to solve some 3-dimensional statics problems.